All right, so last time we ended with coloring our grains from the file called markers. Again, markers just labels each of these grain regions with a number, and that was shown here for the 198th grain and the 239th grain. And so we've gone ahead and labeled all those with colors. We've overlaid it with the original image, and so you can kind of get a good sense for how well we did with identifying the grains. So the next thing we need to do is to go ahead and get some data out of all of these regions. So we're going to go ahead and use the markers again. That's really what defines the grains. The coloring here was really just to make a pretty picture and to check and see how we've done. So the next thing we're going to do is we're going to use this measure region props, or stating for properties, region properties table. Okay, so it's going to generate a table of different properties for each of the markers, each of the grains. And the properties that we're going to measure for each of these grains is going to be contained in our list prop list. And here's our prop list. This is not an exhaustive list. This is just some of the things I pulled out that I decided we'll go ahead and do. So one of the things is label. So it'll tell us for each grain what its label is, what the area of that grain is going to be, what the filled area, which is in our case is the same as area, so I'm going to get rid of that. The a diameter, equivalent diameter. So it'll try and treat the grain as a sphere. Orientation, the major axis length, minor axis length for when they're non-spherical, and the perimeter of the grain. So we're going to just take a look at all of those. The one I'm really concerned with is going to be the area, is the main one that we're going to take a look at. And we'll go ahead and take that data, and which is called props. That's where it goes into. We're going to turn it into a pandas data frame so we can get a nice printout of that from our Panda software. So, all right, just ran it. And so you can see the data here. So the units for everything in here are pixels. So pixels squared for the area, pixels for the diameter, etc. And so we do need to do a pixels to micron conversion if we're going to do something with this data. And so in this particular image, it turned out that the pixels to micron was 0.9. But what you can do is, if you don't have that handy, is if your picture has a micron bar in it. So if you've got a micron bar in here and it's labeled as 100 microns or something like that, what you want to do is go ahead and display your image, and then you want to go and pick off the pixel values for sort of the start of the bar and the end of the bar, and that'll tell you how many pixels there are for whatever the bar length is, and that's how you can get your pixels to micron. To be able to pull off the pixels, what you're going to want to do, I'm going to just pull off this piece here. I don't want to rerun that command. So let me go ahead and put this here. If I want to interact with this so that I can actually read the pixels directly from the image, then remember we're going to need to use this matplotlib notebook. We've used this once before. So if I do that, now I have a live image that I can now run my mouse across, and you can see it's giving me the pixel positions and values. So if I had a bar down here, all I'd have to do is come over and read off the X value for that position, read off the X value for the end of the bar, and just subtract them. And that'd be how many pixels across for the micron bar. So that's all you have to do for that. For the homework, I do have some images for you that have micron bars in them, and so that's kind of what you do. All right, so let me go ahead and close this active window here. All right, that kind of closes it down. I'm going to go ahead and get rid of the notebook command so that we're back to just displaying things in line. And I'm going to delete that one. I don't need it and have it up here. Okay. So that's where this pixels to micron comes in. Okay, so it says pixels to micron, and it's in the units. Let me make that as a comment. Is in microns per pixel. That's the unit. So I just multiply these pixel numbers by this value, and that would change them into micron values. All right. This Greek letter you just saw me use, and actually sometimes shows up in some of the names I might use. You can use the Greeks. The way that you get those is you just type this backslash. I guess this one is. I always confuse which one's back and which one's forward. But we use this one, and then you just type in the Greek, whatever you're looking for. So maybe you really want the Omicron, and then you just hit the tab. Of course, I probably misspelled that. If I just do the slash and hit tab, it'll come up with a menu, so you can actually go through and pick whatever one you want. So here's some of the Greeks that are available: delta, epsilon, theta, iota. These would be a subscript K. What else we got in here? Well, I'll let you. I don't want to waste time here. Upsilon, one of my favorites. Omega. Okay. All right. So anyway, up Omicron. So let me see. It doesn't have an Omicron, just an up Omicron. Let's see what that is. I hit the tab key. Okay, well that's not very exciting. All right. Anyway, mu, hit the tab key, turns into the Greek for me. Okay, so let's go ahead and run this. And here is our property list. All right, so next thing I want to do is I want to go ahead and find the average grain diameter. So I'm going to take my pandas data frame, which is called grain data. Okay. We'll use our dot location command to grab all rows, colon, and the column equivalent diameter. So I'm going to grab all of those, and then I'm going to go ahead and find the mean of that column. So I'll get the average grain diameter, and then I'll go ahead and multiply it by this pixels to micron to turn it into a micron. Okay, and I'm just going to print it out here in my print statement to make my output nice and clean. Then we're going to go ahead and take a look at the same thing now, but we're going to grab the area column instead, find the mean area, and now we're going to convert again to microns, but now microns squared because it's an area, so we have to square our pixels to micron conversion factor, so don't forget about that. And we'll print that out, and then finally we're going to get our grain size value. So let me print these out, and then we'll talk about this grain size value. So here are the results, and this gives me a grain size number of 9.67. Okay, so an average grain diameter of 12.9 is what I got for this sample. All right, the grain size number, we've seen that in Callister in the MSE 2044 course, and in that course you had an equation that looked like this: n equals 2 to the g minus 1, where n here is the number of grains that you would count in a 1-inch square area on a micrograph that was taken at 100x. Okay, so that's the definition of the value n, and then g here is the grain size number we want to calculate. All right, so you can do a little conversion of this instead of needing this sort of funny convention of the number of grains in an inch squared at 100x. If you were to take n now instead, it's just simply the number of grains in a millimeter squared, where the millimeter squared is now at no magnification. Okay, so you would correct for the magnification if it was magnified when you count the grains. But it's just simply the real or true number of grains per millimeter squared of the sample. Okay? And then, so you could use that for your n instead. And then if you were to plug that into this equation and do a little bit of rearrangement, you could find that the grain size number is equal to 3.322 log of this grains per millimeter squared minus 2.9543. Right? So that's the grain size number, as long as n, again, is in grains per millimeter squared. All right, so once I have the average grain area down here, okay, all I'm going to need to do, and this average grain area is in microns squared, because that's our conversion factor. So what I'm going to need to do is change this average area into a millimeter squared, and then just take the reciprocal. So I've got my average grain area, I'm going to multiply by 10 to the minus 6. So that will be my conversion to millimeters squared. And then, so now I have the millimeters squared per grain. If I take the inverse of it, I'll have grains per millimeter squared. And so that's where we get n from. And then we can just go ahead and plug n straight into the grain size equation. And that's all we have to do. We get 9.67. All right, so that's how we can calculate the grain size from a micrograph. And I like this image. I think it really does a great job at picking out those grains. All right, so your job for homework is just to go ahead and pick one of these images, pick whatever you like. These two are the same, except this one's got the micron bar in it. That's a 25 micron bar. So you would use this image just to find out what that pixel conversion factor is. And then you could use this image to actually do your analysis on. I removed the micron bar out of this one. This one has the micron bar in it. I didn't remove it for you. So what you'll do is you could call this in, get your conversion off of that one, and then just crop the image. Just don't take all of the rows. Figure out how many down you have to take to kind of knock off this bottom piece. And that, because since the grains are small enough in this image, that's fine. You'll have plenty of grains to analyze. And then this is the sample that's actually in your Callister text. So this comes right out of the Callister text. And then there's your 100 micron bar. So when you call this one in, you're going to have to do, once you get this micron bar, you're going to have to do a similar thing in that you're going to need to crop it or slice your data so that you're analyzing only the grains, not any kind of boundary that's in there or the bottom. And that's true for any image you bring in of grains. Make sure if there's any boundary around it that you crop that out when you do your slicing. You only want the grains there. And a lot of images have some sort of a boundary around them. All right, part 2. So that's that's the homework, is really just one assignment. For part 2, for extra credit, or if you want a challenge, I haven't actually done this one yet, but I think this would actually make kind of a neat problem, is to see if you can use this technique now, but just grab the white regions from this picture. Okay? And so these darker regions now would all be considered background. So this is where you're going to want the true background that we did in lesson 1, part 1. You're going to actually want there to be a background, and that's, again, these dark regions. And you really only want to analyze the white regions. Okay? And all we're looking for here, if you analyze the white regions and you get the area out for however many it finds in here, they might almost all be connected. Then you could sum them, get the total area, and then if you have the pixel dimensions, you could figure out what fraction then of these white regions are for the whole image. And that's your pro-eutectoid ferrite, and you have the fractional amount of it. So through a little bit of work, you could actually calculate out exactly what the composition of this particular steel is, given that it's just a plain carbon steel. Okay. All right, I guess that is it.